Hello and welcome back to differential equation. We are continuing section 1.6. This is talk on exact equations. It might look like separable, but it's not. We're going to take a look at a differential equation, and we're going to employ partial derivatives from Calc 3 to solve these equations. Now, not too much theory. This is a procedure. So once you learn the procedure, you're good to go. The nature of these problems is two-dimensional, so you don't have to worry about the 3D case from Calc 3. So this is even cheaper on some level. The differential equation will be posed in a somewhat weird way. You will have this function m, that it's a function of x and y, plus n of xy times dy dx, that's the derivative, is equal to 0. So this guy here is actually the partial derivative of f in respect to x. And this guy here is the partial derivative of f in respect to y of xy. So if you multiply through by dx, you get the form of these equations, and they're very easy to spot when they're written in this form. Very easy to spot. So let's take a look. So this is the form of exact equations. Now, what's extremely important is the condition of exactness. So, under condition that partial derivative of m in respect to y is the same as partial derivative of n in respect to x. This is called the exactness condition, condition for exactness. You have to check this every time, because if this doesn't hold, you cannot use procedure for exact equations, because the equation is not exact. So equation is exact when this condition is satisfied. You can rewrite the problem, we'll see how that's done, in that form, and then you just crank the procedure. Bueno? Good. So let's take a look at first example. I'm not going to make anything up, obviously, because it's not going to be exact. Just going to steal from the book. These are already worked out examples. So the first order of business is to check for exactness. So I'm going to find the partial derivative in respect to y of y cubed and ask myself if that's the same as partial derivative in respect to x of 3xy squared. If this equality holds, equation is exact, and I can go on with the procedure. The derivative of y cubed in respect to y is 3y squared, right? Because it's just that. It's a derivative of y. So there are no primes and chain rules or anything like that. And on the other side, you are taking the derivative of x partial derivative of x, that means that y is just a constant which you get to copy. So 3y squared, because the derivative of x is 1, right? And when you multiply 1 into 3y squared, you get 3y squared. Condition holds, therefore this is the exact equation, and we can go on with the procedure to solve it. So, yes?
So you just told yourself partial derivative of x for that part right there, the 3xy squared was 3y squared because the derivative of x is 1.
Yes.
Multiply 3 by 1 and just,
yeah.
That's all that is?
That's all it is. So when you're taking the derivative in respect to x, all y's are constants. You get to rewrite them. Yeah. Great. So what would be the procedure to solve this? You look at this problem up there, and I don't know if it's clear to you, but it's clear to me that if I integrate that, I'm going to get the solution, right? And now we can figure out whether we want to integrate in respect to x or respect to y. Whatever works is fine. So what I'm going to do is I'm going to pick one of these guys and integrate. And then see what I get, take the partial derivative, equal it to the original problem. See the difference, get the constant, and so on. So let's see. Where do we want to begin? This problem, by the way, is not solved in your textbook at all. So I'm okay with solving this one. You can read the next example, which is solved in a book. I'll just pick something else from homework as the second example, so you have another example. What am I going to do here? Well, first of all, we recognize that m is equal to y cubed and n is equal to 3xy squared. Now, what I'm going to do is I'm going to integrate the m in respect to x. So when I integrate y cubed dx, what I get is the integral of xy cubed plus c as a function of y. You must have this constant, but the constant is no longer a number. It's actually a function. Because it could be, this over here could be y squared, for instance. When I take the derivative in respect to x, I'm going to get y cubed, because whatever this function is, whether it's a constant or a function of y, when I take the derivative in respect to x, it's going to go away. So now observe what I have. I have this part here, where I have that this is the function added by some unknown function of y. But look at this part. That's the derivative in respect to y. So what I can do now is take this solution and differentiate that in respect to y. When I do that, what I get is 3y squared x plus the derivative of that unknown constant, which could be function of y. And then I compare this with that. What do I have? I have that the 3xy squared plus c prime of y is equal to 3xy squared. So they're the same. from where I conclude that c prime of y is equal to 0.
What do you end up doing with that 3 next to the n and then you brought it down?
Next to the n.
So if n equals 3xy squared, and then you brought it down, it's xy squared, or xy cubed.
No, this is me just reading the problem. This is the integral, has nothing to do with this line.
Oh, okay.
Right?
Yeah.
When you integrate this in respect to x, you just gain x. Y cubed is a constant which you copy.
Okay.
Right?
Yeah. Oh, I see what you did.
I'll do more examples so it should be clear. So now when I integrate c prime of y, dy, which was a 0, we get another 0. So now what does that mean? That means that the unknown function was 0. Well, you put it at the last step. So answer would be, where's my solution? My solution is right here. So it's x cubed plus y equals, yes?
We just took the derivative, ended up at c prime y equals 0. Then we go to the interval, like reverse it, still end up at 0.
Well, the integral of 0 is 0. Right? The integral of 0 is 0, and then you have plus some constant, I'll put k.
Oh, we're integrating both sides of that.
Mm-hmm.
Okay.
Yes. Why am I writing y? So the solution f is equal to, where's my y cubed plus some constant k. That's the solution. Now I'm going to redefine some values. Calc 3 has much better notation than this. It's convoluted enough?
Well, it's very confusing.
I'm going to work out two examples,
What
yes.
problem was, what number was this? in the
This
book?
was just an example in a book that they didn't solve. They didn't solve this example, so I solved it. I use it to compare, so they cancel, and I see that cy is equal to 0. Well, this is where the solution is. So this is partial solution, which we make better by differentiating it in respect to the other variable. You can start integrating either x or y. It doesn't matter. So whatever you decide to integrate first, you integrate that. Then you take the partial derivative in respect to the other variable. You compare it to the other part, and you figure out. So hopefully we'll have more examples to work on to see. Let's find other examples. All right, let's work on something that is a bit less convoluted to try and make sense out of this. So let's try 34. And then maybe later we can take a look at another one that looks scarier. So 2xy squared plus 3x squared dx plus 2x squared y plus 4y cubed dy equals 0. Bueno? Okay. I am going to call this part by its name, which is f partial x. And I'm going to call this one by its name f partial y. No more m's and n's and stuff. If you want to go with m and m and whatever, you just do that.
Now always do that, try to like break it up into two functions.
Well, they are. They are this.
Renaming it to just give you a better look at it.
Because, yeah, it makes more sense. Now look, guys. What I'm going to do is I'm looking for a solution, which is capital F, right? Now look what I have. I have partial derivative of capital F. So if I integrate this in respect to x, I'm going to get that f, which is solution. Does that make sense? Or if I start on the other side with partial derivative of y, I can integrate that guy in respect to y, and I will still get f as a solution. Now, none of this happens before you check condition for exactness. Because if that doesn't hold, the whole problem is doomed. Now, you can't do it this way. So we check the condition first. And the condition goes like this. The partial derivative in respect to y here, which is 4xy plus 0, is equal to the partial derivative of the second one in respect to x, which is 4xy, and then the second part, so it's good. All right, we got these two equaling each other. Yes.
That immediately failed really good. And there's no other way that we can do it. Say like non-solvable?
No. There are things. Because if this doesn't hold, you have to transform this back into the problem. You write 2x squared y plus 4y cubed is equal to negative 2x y squared plus 3x squared. Oops, I forgot to put dy over here and dx. And now you divide this dx back in here. And then maybe you divide this one over there and get some stuff that cancel. And maybe from that point you get separation of variables, linear, or substitution.
What are the two terms you look at to see that you can differentiate the equal term?
That's in a definition. You have to memorize it. The one that is dx, you take derivative in respect to y, and one that is dy, you take derivative in respect to x. So you just cross them, all right? Good. So this is what we have. We have something that looks like exact equation. You have to check condition for exactness. If it works out, equation is exact, and then you employ the procedure. You are going to integrate fx dx to get f, which is the solution. So that's where we start. So I will integrate 2xy squared plus 3x squared dx to obtain solution for this problem immediately. When I integrate this, remember that x is the variable and y is the constant. So I'll have x squared over 2. 2 and 2 cancels, so I get x squared y squared. Plus x cubed. Plus some function of y. Because I integrated in respect to x. Now, I will write here, solution f of xy is x squared y squared plus x cubed plus c of y. Now this c of y is the unknown function of y. So this is a partial solution. Need to find c of y. That's not plus c, some constant. That's plus some function. So observe that I already have partial solution. Right? I have a partial solution here. And now, what I can do is I can find the partial derivative of y looking at this line and equal it to this partial derivative here. That will tell me what c of y is. So partial derivative of this in respect to y is going to be 2x squared y plus 0 for this term because I'm taking derivative with respect to y, plus c prime of y. So I took the derivative. Remember that c of y is only a function of y, and when you take the derivative in respect to y, you just get c prime. No need to invoke partial derivatives there. Now I equal this to fy from the problem. So on this side, I have 2x squared y plus c prime of y. On the right-hand side, I have 2x squared y plus 4y cubed.
In that previous line, the two f of y now, 2x squared y plus 0 is the constant, 0 is the derivative of x cubed.
Good.
But 2x squared y is the derivative of x squared y squared?
Yes, because the derivative of y squared is 2y.
Right. And derivative of x squared is 2x.
But you're taking only respect to y. It's a partial derivative.
Just pretend
X is a constant in this case.
Just pretend it's a number, and then it will disappear.
It takes time to get used to this. Doing a few problems might flush it out. Well, yeah, yes. Pandora. Over here, I integrate in respect to x because it says dx. That's why we put these, right, to tell us which integration we're using. So when I integrate in respect to x, then I ignore y's. So y squared was copied, and the integral of x is x squared over 2, and then 2 and 2 would cancel. So we get x squared, y squared. On the other side, this becomes x cubed over 3. 3 and 3 cancel, and I get x cubed. So these guys, as you can see, they drop because they are the same on both sides. And here we get, earlier example had that the c prime was 0. Now we get c prime of y is equal to 4y cubed. Right? Integrate in respect to y. Integral of c prime just gives you c of y. On the right-hand side, you get y to the 4th plus some constant k. What you see here is that we obtained c of y. I don't need to factor anything. And that plugs in here. And you're done. Because remember, this line is the solution already. It's just incomplete solution. So the rest after that is you chasing that c of y. So now we found what c of y is. We are going to plug it there and end the problem. I see your hands. I know. I will answer all the questions. Let me just write the final answer for this problem. So f of x, the solution is, go back to the previous one, x squared, y squared, plus x cubed, plus y to the 4th, plus some constant k. This is the answer to the problem, to the differential equation. This is a solution equal to 0, and you can go and do the implicit differentiation and whatever other magic you need to actually plug into the original problem and see if it holds. All right, Alex, you had the hand first. What's up?
Oh, no, it's just nitpicking. I think that's a kappa.
Next question. I'm sorry? This one? So, all right, guys, everyone look at this now. When we took the partial derivative fy of the what we call the partial solution, right? So this one over here is a partial solution. We took the partial derivative in respect to y and obtained this line. Now, this one is the partial derivative of f. But also, this guy here is partial derivative of f. And I equal them. So I pick this one up, and I pick this one up. So as you can see, this over here is there, and this guy is this guy. And when I equal them, because they're both fy, when I equal them, I get this line, the first term drops, and what we're left is this equality, which allows us to compute eventually what C of y is. Kappa. This over here is the solution to your differential equation. Again, we do not have initial condition or anything to compute key. K. Yeah, he's just messing with me. Just because you exist.
You said like 2 weeks ago that it's like a squiggly K or something. I'm thinking of physics. I'm definitely thinking of physics.
Yes, you are.
Okay. Yeah.
Because for a moment I just wanted to see what you're on, because I want the same thing.
He's trying to integrate all classes all together.
Yeah.
Well, we're doing vectors there. We did vectors last semester here. We're doing vectors.
Yes, you're going to do vectors in PreCalc 2, Physics 1, Linear Algebra, Calc 3, Statics. Yes. So you're going to learn the definition of the vector 5 times, because each course is going to say, oh, you've never seen this before. So you learn the same, yes. Learn vectors 5 times from scratch. Now, what I should do is this problem again, starting from integrating here first, and then equaling in the derivative there. Exactly. To show you that you are going to get the same answer. It doesn't matter if you start with fx and integrate in respect to x, or you start with fy. Equation is exact. The partial derivatives are equal. All right? So it doesn't matter which way you're going to start a problem. If you start a problem, because, guys, sometimes it's not going to be pleasant or easy or possible to integrate fx in respect to x. But the other guy might be like this. All right? It might be basic integral on f of x and partial fraction decomposition on fy. Right? You pick which one is easier to integrate, and you do that integral rather than, you know. Yes?
The question was, or I was going to ask, how far into it do you know, like of the course, that you could pick something like that to know that that was the simpler?
You know immediately when you see the problem. Because if you can't integrate something just by looking at it, you don't want to integrate that piece. Let me see if I can.
That's why I know which one's easier or not.
Yes. As soon as the severe migraine kicks in,
Right.
you know you're doing it wrong. Severe, I said. Minor migraines don't count. Some of the pain is expected in this course. Right? Right. This is problem 38. Good luck with certain integration here, right? So this problem is going to illustrate what I just said. First of all, condition for exactness. Is this the same? We will take the partial derivative in respect to y on the left-hand side. When you take the partial derivative in respect to y, derivative of x is 0, that dies. and the partial derivative of inverse tangent is going to be 1 over 1 plus y squared. When I take the partial derivative, so this is condition. When I take partial derivative in respect to x on the left-hand side, I hope you see this. The partial derivative of x is 1. The partial derivative of y is 0, but you have to keep the denominator as is because it was dividing x. This is a very tricky partial derivative for those of you who've never seen partial derivatives before. If it's going to make it easier for you, split this into two fractions. There is a fraction x over denominator plus y over this. Observe that the second fraction, y over 1 plus y squared, has no x, which means that the whole thing dies when you take the derivative. But the first fraction, there is x, and you have to keep its denominator as a constant. Derivative of x is 1, keep the denominator as a constant, plus the second fraction dies completely. So that's why this is the partial derivative, and they're equal, condition fulfilled. We have the exact equation, and now we can go and try solution. Remember that the first part is fx, the second part is fy. Now I should go around and ask every single one of you, what's the integral of? There we go. So you look at this, right, and you say, all right, can I integrate the first one in respect to x? The answer is, of course, yes, it's easy. I have inverse tangent of, yeah, but it's inverse tangent of y, right? So integral of that is just inverse tangent of y times x, because the whole thing is a constant. Whether you have x plus tangent inverse of y, or you have x plus 3, if you're integrating dx, it's the same thing. Completely same thing. It doesn't matter. But let's say you don't see it. Let's say you don't see it. It's okay to start the problem from the fy side, and that's what I wanted to do. Let's say you were terrified, for no good reason, but you were terrified of fx. Sure, start with fy, doesn't matter. So we are going to find our solution fxy by integrating fy in respect to y. You can start your problem this way, which is integral of x plus y over 1 plus y squared dy. Now, why would you do this? Well, you see that you can use u sub, right? You don't have to go do, I mean, you can do trig sub if you like pain, but you can do u sub on this one. And you integrate from there. So now, what do I have here? To integrate this, I have x over 1 plus y squared plus y over 1 plus y squared dy. The first one is x, this one, right, is x, which is a constant, times inverse tangent of y. Remember that the integral of 1 over 1 plus x squared is inverse tangent x. So the integral of 1 over 1 plus y squared is inverse tangent of y. Plus, and now over there, we are going to use u sub. U equals 1 plus y squared, du equals 2y dy. I don't have a 2. I'm going to put the 2 and the 1/2 in. So this works out to be 1/2 u squared. No. It's going to be 1/2 integral of du over u. Much better. So now we are getting x tangent inverse y plus 1/2 ln 1 plus y squared plus c of x. I integrated in respect to y, therefore I need cx function down there, because if I'm to take the partial derivative of this in respect to y, whatever function of x is here is going to die. Guys, this line here is your partial solution. This is over here partial solution. So it doesn't matter whether you pick fx and integrate with respect to x, or you pick fy and integrate with respect to y. You are going to get partial solution to this. Now, once you have the partial solution, you will differentiate using partial differentiation. You will differentiate in terms of the variable that you did not integrate in respect to. So, since I integrated in respect to y, I am going to find the partial derivative in respect to x of this x tangent inverse y plus 1/2 ln 1 plus y squared plus c of x. And before you freak out, realize that you're taking the derivative on x and all the y's are constants. So the partial derivative here, partial derivative with respect to x, is just 1. So you're getting the tangent inverse y plus the whole thing over here dies, is just 0, plus c prime of x.
No, it's x plus tan, or tan. It's not x times tan, or it's roll back up. Okay.
This is a constant that you kick in front, so it's times.
Oh, okay, okay.
The plus is the second term, which is the second term, which is our ln term. So yeah, it is times.
Question.
Yes.
And then, can you, after that second to last line, what did you say after? You're taking the derivative of x, and you're not touching the y, right above this.
Yes.
tangent.
So this was the partial solution.
Yeah.
And now we're taking the derivative of that partial solution in respect to x, because we integrated in terms of y. And this over here, now we're taking the derivative in respect to x, y is a constant. So this is like, this term here, the first term is like 2x, all right? Or like 5x. So the derivative of 5x is just, derivative of 5x is just 5, right? That's technically what's happening here. The derivative of number 7, let's say, because there are no x's there, is 0. And the derivative of unknown function in respect to x is that function prime, right? So this part here is fx. This is what fx is equal to. But I also have another fx in the original problem, which is this puppy here. Equal them together. So I have tangent inverse of y plus c prime of x is equal to x plus tangent inverse of y from original problem. These two cancel out, and what I get is c prime of x is equal to x. Hit this with the integration on both sides. And there is your c of x, which is what we were after. This is x squared over 2 plus some constant k. We go back to our partial solution and replace cx by the cx we just found, and the problem is solved. So f of xy is equal to x tangent inverse y plus ln of the square root of 1 plus y squared plus x squared over 2 plus k. This over here is the solution. This is general solution. I had 1/2 in front, so I brought it in as the exponent and becomes a square root.
If we don't do that, we can take points off?
Of course not. Unless you want me to.
I don't want him to take points off, I'm sorry.
You sound sarcastic.
Don't do that to me.
Now you're making him doubt. I will not take points off.
Okay.
You're welcome. Now I'm making doubt again. Yes?
So if you had an initial condition, you would be looking for 10.
Yes. The whole thing is equal to 0. And you will be plugging in x for x, y for y, and the only variable would be k. Since you guys love this so much, let's do another. Well, just you can practice. I can't teach the next lecture in
Half an hour.
yeah. So maybe practice some more.
For page 73, is there still on 73?
So I'm still on 73. Yep. Are you ready? Excellent. Problem 37. You're going to love this, I promise, because the functions are user-friendly. We have cosine x plus ln y dx plus x over y plus e to the y dy equal to 0. See? Nothing to worry about. This is problem 37 in your textbook. Cosine x plus ln y dx, x over y plus e to the y dy. This is the time when you talk to your friends in the class.
Friends?
Sure.
Do I have to?
I understand your situation.
Did you lose the race? Yes? Hey, you were very welcome. See, I'm very accommodating on Tuesdays. Thursdays, not so much.
So talk, figure out, do the problem.
These pairs, these pairs.
Yeah, X first. Is it always like that? Professor Ted, is it always? Yeah, is it always FX and FY? Always.
That's set in stone. That's set in stone. Yep.
Cosine, negative sine, negative
Well, we have a cosine x and which is
which is
You integrate in the same, you differentiate the opposite. Wait. Condition.
yeah,
You will always differentiate the opposites in equations. 1 over x plus 1 over y plus 1 over x plus 1 over y plus 1 over x plus 1 over y 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 plus 1 over y
Well, the entire part.
Battery over here.
Yeah, it's gonna equal because the derivative of ln y would be e to the y.
Right.
What's the derivative of cosine? Negative sine. What do you want to do? Partial derivative of first condition, see if they're equal.
Oh, dude, okay, so, yeah, ln y, the derivative of that is e to the y. Right? Plus, so this one is right, yeah, 1 over y. 1 over y equals, this is e to the y, so you're looking at y is the 1 with the x, which that just, so that is good with that, that's 1 over y. Wait, do we do the derivative because it's the y, right? I don't know, it's so much Chinese stuff.
Who's it count?
Which one is easier of the two to do? Left side or right side, what's the car?
I hear people saying they're dealing negative sign about what's the George has a tractor? Is your first page used? Yeah, but I have a compass pack. So here, right? Yeah. When you drop that down, I got the x, right?
And we're trying to equal this side.
Right, so you took the derivative of this.
Yeah. To come up with that.
Right.
Which automatically, when you break this up, when you take a derivative, it knocks out this part. That's how.
Right, well.
Derivative of x is 1.
Right.
1 plus 1 over 1 plus y.
Right, so that's like the same thing, right? So you look at the inverse, you look at ln y, and that's just 1 over y, and then you took x.
Oh, ln y,
The derivative of that is
1 over y.
Yeah.
I thought it was e to the y.
Yeah.
1 over y?
Yeah.
Sure?
Yep.
Negative sine x? Plus 1 over y.
Well, do you take the derivative of the cosine x as well? I thought you leave that the same. Because I thought we're only taking the derivative of the y term. Oh, okay. That's how it goes. So we figured out the equal, okay.
This was x with respect to y, and this is y with respect to x. See, why did he drop the y?
Because he split these two up.
Yeah.
I have no clue. I haven't done it,
Why
but
did the x drop?
looks nice. This is equal sign, right? Or no? It's x? X times ln x?
Yeah.
I need equal sign there. But
Oh,
okay, so this is where you did it?
Yeah,
Nice.
that's not presentation ready.
But it makes sense. Oh no, wait, this is 37.
Start here.
Yeah.
But if I label them, that helps. Label.
Yep. And then you decided to integrate this one.
Yeah.
You need parentheses there. So ln y, you need equal there. But yeah.
I figured because then the e to the x is going to be.
Yep.
How Maria did over the summer. I think there was too much going on because it was too concentrated, and I think she did it completely that way, but it never sunk in how to do that.
Yeah. Yeah, that was in chapter, I believe it was it's 14.3 or something like that.
I was over at work.
All right. Let's take a look at the solution of this problem and then do another one and then disappear into the night. We are going to check the condition for exactness. Partial derivative in respect to y is 1 over y. And on the second one, partial derivative in respect to y is also 1 over, no, partial derivative in respect to x, sorry, is 1 over y. So condition holds, equation is exact, and we can unleash our method. Now, you have a choice to either integrate fx in respect to x or fy in respect to y. It doesn't matter which one you work on. So which one do you want? Should we integrate fx in respect to x or fy in respect to y? Let's see, what's the consensus, or should we vote? That doesn't work.
fx with respect to y, that doesn't work?
No, it's either fx integrated in respect to x or fy integrated in respect to y. Okay. So we are going to start looking for our solution by integrating cosine x plus ln y dx. When I integrate this, integral of cosine is positive sine plus x ln y, because ln y is just a number in eyes of x, so it acts as a constant, and when you integrate you just pick up x. So you can think of ln y as 3, and then the integral you get on the other side is 3x, plus c in respect to y, because we integrated in terms of x. That extra constant could be a number, but also could be a function of y, only y. This over here is already partial solution. All we need to do is to determine what cy is. Well, we take the partial derivative in respect to y and then equal it to, yes, fy from the problem. So partial with respect to y, sine dies. Derivative of ln y is 1 over y, so we have x over y plus c prime of y.
So we switch it back, doing everything in respect to y. Because before we did everything in respect to x, right?
Yeah.
Okay.
So now we are going to equal this to fy from original problem, which is x over y plus e to the y.
So the x's over y's, they cancel.
Yep. So these drop. And from there we get that the c prime of y is equal to e to the y. Hit this with integration in respect to y. And we get that c of y, which was what we were after, is e to the y plus k. All I need to do is to plug that in the solution because we were looking for c of y. Now we have it. And the answer is sine x plus x ln x, no, x ln y plus e to the y plus k. And that's exactly what you had, which is great. And that's the solution. So this one is general. We have time for one more.
Can it be one?
Well, it's going to be one where you have to do. So I want to see, I don't know, but I want to see if this problem can be solved this way.
So if we have limits, we can then figure out the partial solution.
Y prime equals negative and then the fraction. Numerator is y times quantity 2x cubed minus y cubed divided by x quantity 2y cubed minus x cubed. I actually don't know if this will work, but look at this problem, right? Yeah. Yeah. Which means that the one before is probably exact equation, which is what I want to check. So what I'm going to do here is I'm going to write dy over dx is equal to this thing. I'm going to actually assign negative to numerator. So how about negative y 2x cubed minus y cubed over x 2y cubed minus x cubed. And you know what? When I distribute this minus sign, it will swap these guys. So what I'm going to do now is I'm going to cross multiply these. So I will have x 2y cubed minus x cubed dy, right? Times equals to negative y 2x cubed minus y cubed dx. And now I move this to the left, and you can see that the problem is in the form of exact equation. Then FOIL, right, the y and x. Multiply by y, we get 2x cubed minus y to the fourth dx plus 2xy cubed minus x to the fourth dy equal to 0. So what we did is we converted differential equation that was given to us into exact equation, which probably your problem number 5 can be solved that way. We are going to check when we're done with this. Just start it, and then you guys can finish it off. Yes.
That start of the line, shouldn't that be 2x cubed y minus y to the fourth?
There is a y there.
Oh, sorry, I wasn't paying attention.
Thank you. So now when we do the condition, right, hope this works. Differentiate in terms of y on the first one. We get 2x cubed times 1 minus 4y cubed. The second one you should differentiate in respect to x. You get 2y cubed minus 3x, 4x cubed, and you see that it doesn't work. Not exact, can't solve it using exact equations. It looked good and then failed. So this is the reason why you must check the condition. Now guys, if you try to push to solve this with exact equation procedure, you will see, you open the gates of hell and all kinds of stuff falls out.
But it can't be done.
No, because once you integrate in respect to x up there, when you differentiate in respect to y and you equal it to that other side, stuff doesn't cancel. That's why condition for exactness is important. Yeah, we're not checking the condition just because it's an extra thing to do. It's cool and awesome. It actually guarantees that the problem can be solved, right? But I am interested in number 5. I want to go back to problem number 5, which possibly was something that we could solve using this method. So what we had when you distribute this thing was x squared plus xy, I'm distributing now, dy dx equals to, so this is number 5. I'm just trying. No guarantee here. Xy minus y squared. So this is what we have for the problem. Now I move dx to the other side. We get x squared plus xy dy is equal to xy minus y squared dx. Now we move dx term to the left-hand side. We get negative xy minus y squared dx plus x squared plus xy dy equals 0. And we take this negative sign inside, which changes all the signs. So I'm going to swap the terms. And this is the final stage before we check the condition for exactness. If the condition holds, then this method, exact equations, will solve the question quickly for us. Let's check. So now condition. Take the derivative in respect to y on the first one, you get 2y minus x. On the second one, you get, in respect to x, you get 2x minus y. Yeah. Nope.
You don't get 2x minus y there. No, that's plus y. Wait a minute.
When you take the partial derivative in respect to y on the first one, you get 2y minus, the derivative of y is 1, so just minus x. On the other side, you're taking derivative in respect to x, so it's 2x minus y, and they're plus y, yeah. But still, yes. Still, it didn't work. Such is life, right? So your method of factoring prevails. Recommendation for you guys is to go back to problem number 5 and try to factor out x and redo the entire problem. It might work out nicer in terms of the solution than what I did in class. So now 1.6 is complete. Next class, definitely 1.7, and then we'll try to peer into 1.8. The exam 1 should contain both chapters 1 and 2 on it, because we are having 3 exams and we have 7 chapters or so, something like that. So exam 1 is all of this stuff, chapter 1, and then chapter 2 with undetermined coefficients and stuff like that. And then chapter 2, the exam 2, holy nightmare, it's going to be Laplace transforms and power series. So chapter 3 and chapter 4, which means a lot of partial fraction decomposition, a lot of by parts, and obviously power series with all of their intricate works.
What's the percentage of failures of this class?
Hmm.
You work hard, you'll be fine. Yeah, we do work hard.
All right, bye.